Hi, class. We're going to talk about comparing two samples, and we're going to look at two different types of tests, the two samples means test and two sample proportions test. And it's very much like what we had done before with hypothesis testing. And we just want to add a few things in here. But if you have two samples, those two samples are either going to be independent or dependent. And again, we're just assuming it's either going to be one or the other. And there's lots of all kind of different possibilities out there, but for our case, again, we're just going to compare one against the other. And if you have two samples and they're independent samples, independently generated in a sense, is what you do is you have uh, two samples and you have two different groups that you're comparing. Okay. So if I wanted to test to see if doing uh, statistics online was the same as doing statistics in a classroom, I could run a two sample independent means t-test. And what I would do is I would pick two different groups. I would have one of my classes that met online for the whole semester, and so that'd be one of my groups. Then I would have a totally different group of students, and I would have a group that had only learned online the entire semester again. So that would be, and that's a very, very common test. And now, if we have dependent samples, though, we can also run what we refer to as a two sample t-test. And that's if you have one group, okay, one group, but they're tested twice, okay. So it's, again, one group tested twice. So let's say that um, we wanted to see if a weight gain powder, maybe for teens, they want to play football and they want to gain some weight, and so you can buy powders, and they say if you drink this powder in the morning and then eat normal the rest of the day, that you eventually will gain some weight. And what we would do is we would have one group of teens and we would test them before we started the experiment, before they started using this weight gain powder. And then we would test them at the end, or in this case, weigh them at the end of the study. So we may run the study for 2 months. And so at the beginning of those 2 months, again, we would weigh all the teens, one group of teens, get all their weights, and then we would let them, you know, drink this protein drink with this protein powder in it for those 2 months, and then we would take that same one group of um, teens that we had, and then weigh them all again, and we would compare their before score and after score. So a lot of times, people call this a pretest, post-test design. And again, pretest meaning before the treatment, they're tested, and then after the treatment, they're tested. So they're both good designs, and it all depends again on what you're really trying to come up with. And this weight gain powder idea would be a good reliable test. Okay, and so let's go ahead and erase this. We're going to look at an example first of a dependent test. I'm going to clear the canvas, and then let's see if I can. This calculator will stay up. Maybe, maybe not. Okay. So there's lots and lots of examples out there of where you might want to run a pre-test, post-test design. For example, NASA, you may have heard that it's supposed to be good to put plants in your house, and they are supposed to eliminate certain types of pollutants in the air. And what NASA did is they tested the air in the biodome. They tested what they call the VOCs, the volatile organic chemicals, and they then put plants in the biodome for 2 weeks, and then they measured the volatile organic chemicals again after they put these plants in there. And so again, they measured before the plants were in there, then they measured the air after the plants were in there, and then they found out that, yeah, that plants do really reduce these VOCs, which are typically measured when they're looking for, like, say, sick building syndrome and so on. So, important study. And they continue to study maybe which plants are best and so on. But we're going to take a look at a study that was done on hypnotism. And remember that we have to set up the hypothesis and see what we're doing here first. So we're one to have a null hypothesis, some h sub 0. All right, and we're going to write something here, and then we're going to have this normal curve that we draw, and we're going to use it. We're going to assume, right, this is a sampling distribution, and we're testing the mean difference, okay, in a before and after treatment on hypnotism. So again, what this study had done is they felt like hypnotism would reduce the feeling of pain. And people use hypnotism for different things, maybe lose weight, help them quit smoking, uh, and lessen anxiety if they were going to do like public speaking or something. And then, but this particular study was on to reduce the feeling of pain. So the null hypothesis, this is a little bit different than what we had done before. There's no claim other than that hypnotism will reduce the feeling of pain. So if it doesn't work, that means that the mean of the differences is going to be equal to 0. Okay. 0 meaning, again, no difference between the pre-test feelings of pain and the post-test feelings of pain. Okay. So let's put up here a table. And when I straight line, and this is subject, and we have A through H. We have A, B, C, D, E, F, G, and H. So we have 8 subjects, and they had a before score or a before feeling of pain. Let's see if I can get this a little bit straighter. And then after. Now, again, the before means before being hypnotized, after being hypnotized. So what they did is subject A has 2 scores. So in a dependent test, we have one group. Here's our one group. They all get tested twice. They get tested before hypnotism and after hypnotism. And so I'm going to put in these values, and you're going to need to put these into your calculator, and I'll just get to that in a minute. So 6.6, 6.5, 9.0, and 10.3, 11.3, 8.1, 6.3, 11.6. Okay. Again, those are the before scores. And then the after scores, 6.8. This is a rating scale from 1 to 12. And B is 2.4, 7.4, 8.5, 8.1, 6.1, 3.4, and 2.0. All right, so now we're going to put these into the calculator too. So I just wanted to make sure I had them up here and here because this is going to kind of go away when I start writing. But what we do is you're going to go into stat and edit. So we're going to hit enter. All right, and we have L1 and L2. So the before scores will go in L1. So again, it's just going to take a little bit of time. 6.6, enter. 6.5, enter. 9, enter. 10.3, 11.3, okay, 8.1. Oops, I got a mistake here. 11.3, enter. And 8.1, enter. 6.3, and 11.6. Okay, so I'm just going to take a quick look again. We have 6.6, 6.5, 9.0, 10.8, 11. And it looks like got that column in right. And we're going to put in the 6.8, 2.4, okay, let's double check these. So we should have pairs. This is paired data, and they all should match up. They got to be in the right pairs because each subject, they have a before and after, and we're going to subtract those and look at the differences. Our null hypothesis up here is that the mean of the differences between the before and after scores. And this is a good design when you have issues with measurement error, which in this case we do because each subject got the same amount of shock. So they just put a little electrode on their finger and shocked them the exact same amount. And if we didn't do this kind of test where we tested everybody against themselves, you'd see what would be happening. Look how much error there would be in our results. Because if everybody got the same, and they're reporting way different amount. 11, this is 6. So we really wouldn't be able to analyze the results at all. Now, we have the differences here though. So really what's going to happen is we want to compare the differences. So these two columns, even though they do tell us some stuff, so we always want to look at data. This first person actually said they experienced more pain after hypnotism. And the rest of these at 6 down to 2. So there was a pretty big drop, a little bit of a drop, some there, a drop, and nice, and then there was a big drop here. So people seem to experience the effects of hypnotism differently, which is what we would expect. And again, statistics, we always have to remember there's variability in what really goes on out there. And so we are seeing, a lot of variability in the effects of hypnotism. So we're going to test only the average difference, right? The overall difference. And we assume it's 0. So why do we assume that? Well, again, remember that it's innocent until proven guilty. So basically what we're saying though here is that it doesn't work. And hopefully we can find enough of evidence to say that it really does. And that gives us confidence then. Because if we only had a little bit of evidence to claim that it worked, we wouldn't feel very confident about that. All right, here's kind of a tricky thing here. Let's go over to L3. Okay, I go over to L3 and go up and highlight L3. And I'm going to type in L1, which is that little one right there. So you see L1 showed up here, minus L, the second function, the number 2 key right there, L2, L1 minus L2 equals. So you see what we did is that L3 automatically put in all the differences. So I can see the variability in the differences. Okay, I can see the variability. And then what I want to do is then I don't really care about these columns right now. All I care about is this one column, the differences. So we are going to run a one sample t-test. So one sample means t-test. All right, so now we're back to, remember, a one sample means t-test is number 2 on your calculator. Now, before I do that, I need to decide, am I going to run a 2-tailed test? Well, we could. A one-tailed test is better. It has more statistical power. It cuts our p-value in half. Remember, the p-value is the probability of a type 1 error. So we can cut our probability of a type 1 error in half, run a one-tailed test. Now, I'm going to put this over here. Why am I doing this? Why a right-tailed test? Well, we know why a one-tailed test, right? It's better. Why a right-tailed test? Well, it's kind of basically depends on the software, the calculator, whatever you're using. But I put this in as in L1 minus L2. L1 means before hypnotism, so we're assuming lots of pain. After hypnotism, less pain. So a big number minus a smaller number, these should be all positive, theoretically speaking, which means over here. We're going to end up over here. Okay, so that's where we're in it. Test. So let's go ahead and hit stat. Okay, oops, got to go back up to here. Our null hypothesis then is that the mean of the differences is going to be what? Less than or equal to, right? Less than. Well, why do we pick less than? A lot of people get confused on that. Remember the big part, less than all this or equal to all this, and then the alternative is up here, significantly greater than. Okay, that's that backwards kind of thinking. So let's go to stat, test. We're going to run number 2, a one sample mean t-test. The data, I got to put in the data. Well, it's in there already, right? Hit enter. Okay, where's the data at that we want? All right, the null hypothesis, first of all, is 0. Okay, right there, 0. And then the list is we are in L3, right? Now this thing, we're running a right tail test. Yep, it's over on the right. There's the right shaded part, right? Okay, and then we can get down and calculate. Okay, so let's look at the results. We've got T is 3.035 and P 0.0094. Here's my sample mean. So of the differences, the values that are in L3, that's the average difference. This is the average standard deviation. And then my sample size. So the sample mean, again, we're testing one sample mean, even though we're calling it a two sample mean test because we really started out with 2 samples and then we created one. And this works fine to be able to do it like that. So what's this t value? Well, your t is your number of standard errors. So the distance from 0 up to this point right here, 0.3125, okay. This is 3.125, right? That's my sample mean. So the distance from here to here is 3 standard errors roughly, 3.0359. So roughly 3 standard errors from here to here, which means, remember, standard errors, if you're past 2, you're out there. If you're past 3, you're really out there. So this is a big difference, statistically speaking. In terms of numbers on the pain rating, it's 3. It's a difference of, on average, about 3 units. So these differences from here to here to here to here vary, but on average, people experienced about 3 less units of pain on their rating. And okay, our p-value, right? That's an important. So what is the p-value again? Probability of a type 1 error. If we reject, right? That means wrongfully rejecting the null hypothesis. So 0.0095 we'll put here. So this 0.0095. That means that's what? That's less than 1. That's about 1%. So this area right here is 1% of all of this area. It looks like it's more, but it's 1%, right? So that's good, right? That's really good. We're starting to feel pretty good about our conclusion. So p-value, there's our average. And what's this 2.9 telling us? The numbers are only 6 and 7 and 9 and 11, so they're not very big numbers. And our standard deviation, if we go 2 standard deviations above and below, that's like 6 units roughly above and below. That's a lot. So that means there's a lot of variability in how people are affected when they get hypnotized and with respect to, feelings of pain. So, and then there was a sample size of 8. We had 8 pairs of data here, right? All right. Well, we need to conclude. All right. Remember that the rule is if p less than alpha, reject h sub 0. Well, I don't have a p-value up there, but let's go ahead and throw one in. Let's say, or an alpha. I'm sorry. My p-value is right there. 0.0095 less than what? Well, let's let alpha equal 0.05. That seems to be reasonable. That's the standard. So point oops, 0, 5. So P is less than alpha. We are going to reject this statement up here that the mean difference is less than or equal to 0. We can accept the alternative that it's significantly greater than 0, which we see it's up here, and we said it's like 3 standard errors. So yeah, so everything's working out and telling us that we have pretty good confidence. It's kind of like we have a 99% confidence interval in a sense, because this is about 1% of chance of error. So we're roughly about 99% sure about. Go ahead, let's reject, because we do have evidence to show that hypnotism does help reduce, right? We're reducing these numbers from before to after, lessen the feeling of pain. And I'm going to stop on this video. I'm going to make these videos a little shorter, even though it's still roughly about a half hour, because the problems, they are longer. And then I'll do a couple independent means will go a little bit faster. But this one took up some time because we had to put the data in. And on the test, you'll have to put the data in. You'll be given a table, and you'll have to put in L1, right? L1 before L2, and then you'll go in and do L3 is L1 minus L2, and you'll get your differences in there, right? So let's go to stat and edit and see. Yeah, there's our data. So you'll type these in, get it to put those in, and then you'll do the test number 2, right? The one mean t-test. Okay, so we're going to end this one video with just that one problem, and then I'll do another one on the independent means and proportions.